Welcome to this first lecture of RFIC design. So as customary, we should not start off with an acronym. So what does RFIC stand for? RFIC is more popularly known as or referred to as radio frequency integrated circuit. And what is this course about? We'll be dealing with design of radio frequency integrated circuits, right? So one at a time. So this course is a circuit course, right? That goes without saying. But more importantly, this course is about integrated circuits. It's about IC design, right? So when I say integrated circuits, what do I mean? I'm not talking about discrete amplifiers or discrete transistors that you get and you put them together to make an off-the-shelf component. Here we will be talking about circuits which can be put in a substrate, in a wafer, right? And it can be batch processed. And more importantly, this particular course will focus on CMOS circuits. So ideally, the subtext of this course is it should be CMOS integrated circuits. Even though we call it an RFIC design, in the back of your mind, you should always have this at the back of your mind when you are going through this course, and it will become obvious in the future lectures that we will be mostly concentrating on CMOS based integrated circuits. Having said that, the concepts that we will be going through in this course will be ubiquitous, right? So the concepts that you will be using in this course can be used for a BJT based circuits, or tomorrow if you want to make the same designs in FinFET, these concepts will be useful in those type of circuits as well. Okay. Now, what about the other two terms? What about radio frequency? So radio frequency refers to the fact that we are talking about a certain range of frequencies, right? A certain range of frequencies which fall in the which are of a much higher frequency than whatever we speak, right? Radio frequency typically refers to a few kilohertz to few gigahertz frequency range, right? So in this course, we will be particularly interested in learning about radio frequency CMOS integrated circuits, and not only learning, as in not only having a circuit and analyzing it, we will learn how to design this RF circuits from scratch. Okay. So now, before going into the details of RFIC, which we have the entire course dedicated to the same, let me start off with some very intuitive real life examples, right? And try to convince you some of the intricacies that RFIC design will some of the intricacies which we'll encounter in this course, right? So for the time being, let us forget about the fact that it is an electronics course. Let's assume that we want to communicate, right? So there is a person A. Let's say there is a person A and there is a person B, and they would like to communicate with each other. And one would like to communicate over voice. So person A speaks, right? Person A speaks and person B listens, right? Similarly, at certain instant of time, person B speaks and person A listens. So when somebody is speaking and somebody is listening, obviously we make the assumption that the speaker intends the listener to listen to speaker intends the intention of the speaker is that the listener would be understanding whatever the speaker is saying. So in this case, when speaker A is speaking, the intention is the speaker B will be listening, and when speaker B is saying something, the intention is the speaker A will be listening to it. But now let's, from the simplistic real life example, let's try to see what are the unsaid protocols that we follow. So number one is can speakers A and B speak simultaneously? Obviously no, right? So what's the problem if speaker A and B speak simultaneously? Both of them, I mean, nobody is listening to each other, nobody is hearing each other. So I might be thinking that I am making perfect sense, but why is B not listening? Or B might be thinking I'm making perfect sense, but why is A not listening? The whole problem is both of them are speaking simultaneously. So what is the solution? What is the easy solution? One solution can be that speak one at a time. One at a time. That is, you decide that this is the time slot in which speaker A will be speaking or transmitting, while speaker B will be listening or receiving. And there is a separate time slot in which the speaker B will be talking or transmitting, and in that same time slot, speaker A will be listening or receiving, right? So this is typically in communication jargons, this is called time division multiplexing. This is called time division multiplexing, right? So now there is another way of also communicating instead of speaking one at a time, but that is slightly different in the sense that let us assume speaker A and speaker B are not speaking in the same tone. For example, let's say I speak in a very shrill tone, right? I have a very different frequency of my voice is emanating a different frequency with respect to somebody who is speaking in a very low frequency, who has a high bass, right? So I mean, unfortunately, I'm not gifted with making different types of sounds. But let's say if you can imagine that speaker A speaks in a very high frequency tone, right, a shrill voice, and speaker B speaks in a very low frequency tone, right? So then there is a possibility, right, the speaker A and the speaker B can simultaneously talk and also listen to each other. Granted, it's not an easy thing to do, because ultimately while speaking and receiving we are using probably the similar part of our brains, but in principle both of them can speak and listen to each other, right? So this is often referred to as, I mean, frequency division multiplexing. That is, if both of them are speaking at a different tone, then there is a chance that both of them can speak and be able to comprehend what they are saying, right? So what is the solution? The solution is speak in different tones. So this is called frequency division multiplexing. As it turns out, you must have taken undergraduate courses in which these concepts of time division and frequency division multiplexing have been referred to in a communication protocol, but they need not necessarily be limited to electronic transmissions, right? Okay, so this is forget about speaker A and speaker B. Now think of, this is a cell phone, right? So instead of speaker A, assume that you have a cell phone 1 with lots of buttons and all. This is cell phone 1, or let me say mobile phone 1. And you have another with a mobile phone 2. And speaker A, instead of shouting at speaker B every time, what is speaker A trying to do? It will be dialing something on your mobile phone and on MB1, and speaker B will be listening, or the person B will be listening through MB2, right? So exactly the same protocols apply. That is the speaker, either the cell phone 1 or the mobile phone 1, right, will be tuned to a different frequency than mobile phone 2, right? So as you are going to see, exactly the same protocols apply in electronic communication systems also. So in this course, we are going to talk about some communication protocols, right? So what are you going to learn? We are going to learn about, what is the agenda? We are going to learn about communication protocols. Okay, fine. What is the next thing that we are going to learn about? So if I go back again, so now let's take the example of, that maybe the speaker A and the speaker B are not, or the person A and the person B are not very closely located, right? Person A is probably sitting one end of the class, person B is probably sitting at the other end of the classroom, or maybe in the other end of the field or something, and they are trying to communicate. So what happens if two people who are trying to communicate with each other verbally are spaced, geographically spaced at a different location? So naturally, the strength of the voice, the strength of the sound that will reach either from speaker A to speaker B, or speaker B to speaker A will be very feeble, right? So the power of the signal that you are going to receive will be very small. So what happens then? What's the problem? The problem is, let's say you are indulging, let's say at this point of time, speaker A is speaking and the person B is listening, is trying to listen, and this person B is located far away from speaker A. So naturally, the voice, the sound that reaches the eardrum of speaker B will be very feeble. Now, what is feeble? When I say very feeble, I am essentially saying that the waveforms are very small, or the sound amplitude is very small, or the sound power that is reaching the eardrum is very small. But small compared to what? It is small compared to any other disturbances that speaker B is encountering, right? So what disturbances speaker B might encounter? Let's say I am chewing something, right? Let's say I am B, and I'm sorry, I'm referring to as speaker B, but it need not necessarily be speaker B. In this example, B is the listener. So let's say I am B, and I am chewing something, right? So basically, there is a sound the sound of my of me chewing some food is also a disturbance that is disturbing my eardrum, right? Or maybe I am listening to a music that is probably going on in a separate room, or maybe I'm indulging in some activity which is also generating some additional noisy sound, right? So what happens then? Then obviously the sound that I am supposed to listen to, from the message that I am supposed to get from speaker A, who is at the other end of the field, right, is, even though it is reaching me, it is much feeble than the sound that is around me, right? So it's below the baseline sound. Hence, I might not be able to even understand or even comprehend that speaker A is trying to get in touch, right? So what can I do? So if I know that I am supposed to receive I am supposed to listen to speaker A. What do we normally do? We try to block out all the sounds that we can, right? And try to concentrate really hard. Or try to hear what speaker A is trying to communicate. So what does it mean? It means that I'm trying to suppress noise in the surroundings, and I'm increasing the sensitivity of my eardrum, right? And how do we normally tend to do that? We basically stop doing any activity that adds more noise, right? So same thing goes in case of electronic communication. So we need to ensure that our receiver has very small noise or very small additional noise. Why do I say additional noise? Even if you take the example of two people talking to each other, you will obviously understand that you cannot ever make the noise to zero, right? There is probably some air blowing, there is some, even at the most silent of environment, there will be some datum level sound that you will experience, right? If nothing external, you are going to probably be experiencing the sound of your breath, right? For example, so that is an additional noise. So when you are designing an a receiver circuit, you have to ensure that the amount of noise that the receiver circuit itself is generating should be sufficiently small, right? So then what we need to learn before we get into designing receivers, we need to learn about noise. So we need to learn about noise. We will learn about types of noise, right? And then we learn about, this is types of noise in electronics, in CMOS systems, CMOS devices. And then we learn about how noise propagates in an electronic system, right? So it is not only necessary for us to understand the origins of noise, we also need to understand, okay, there is some noise, but how does it eventually affects our signal, right? So that is what I mean by how noise propagates in an electronic system. Okay. What else? So now let's concentrate on, let's go back to the same example. And now forget about the receiver, let's talk about the person who is trying to communicate, right? Who is trying to transmit, right? So let's say again, A and B are far apart. I am A, I am trying to transmit, I'm trying to speak. So what should I do? I should be speaking as loudly as possible, right? At the top of my voice, at the peak of my voice. So I'm sure if you have tried this, you must have tried this at some point, some time or the other in your life. When we try to shout, our voice kind of breaks, right? So the fidelity of the signal, or the fidelity of the words that we normally speak in a cool and composed manner, it kind of gets distorted, right? So our voice gets distorted, and probably the words that are supposed to sound in a certain way, they do not sound in that way, right? So essentially what ends up happening is that instead of generating the particular tones that our vocal cord is supposed to generate, it is generating more or less that tone, but certain other tones also. And you might have encountered these examples also when you try to increase the volume of your microphone, not the digital ones right now, but if you really turn on the volume of the microphone or your FM radio, you are going to see that okay, the decibel levels go up, but they don't necessarily lead to a very pleasant experience, right? So what happens? What is the cause of this? So this essentially causes distortion of the voices, right? So essentially we are going to see that, or I should say, high power transmitters we will see that high power transmitters lead to distortion of signal. Now, distortion is a technical term, right? But we leave the technicalities for later lectures. But for the time being, we try to understand that what is happening. We are essentially saying that if I am trying to communicate with a very large power, right? If you are trying to send out large power, just like our human voice gets distorted, electronic signals will also get distorted, right? Because ultimately, whatever is blasting out the power will probably not be able to blast it out, right? So what we need to learn, we first need to then learn, right? We need to learn distortion. We need to learn how to sources of distortion, or in other words, we need to learn large signal characteristics of CMOS devices. Or simply put, we need to understand the large signal characteristics of amplifiers. Similarly, we should also learn the effect of distortion on signal propagation, right? Okay, so till now I basically have been trying to motivate why do we at all need to do learn RFIC, and if you need to learn RFIC, what all other things also we need to done before we get into actual design of these amplifiers, right? So to recap, what did we see? We need to understand how communication. We need to first establish what are the communication protocols, right? And once we have established what are the communication protocols, we need to understand what are the bottlenecks for a receiver. And we understood, at a very 1,000 feet level, we understand that the receiver should be able to receive very feeble signals, which means that it should handle extremely low amplitude signals, or in other words, it should not be adding more noise to its to the signal that is receiving, right? That is as far as the receiver is concerned from a very 1,000 feet level. And also we probably need to understand how a transmitter behaves, and if we want a transmitter to communicate with the receiver from a far away distance, we'd like to ensure that the communicator is able to blast out very high power, right? But at the same time not distort the signal, right? So essentially we need to understand how to characterize noise, what are the sources of noise, how noise propagates, and we also need to understand how to handle distortion on the large signal performance of a circuit, and how does distortion affect your signal. Now, in order to learn both this noise and distortion, we need to be comfortable with the frequency domain analysis of signals, right? So we need to be comfortable with frequency domain analysis of signals, right? So when I say frequency domain analysis, what do I mean? I essentially mean that we should be comfortable with Fourier series, and we should be comfortable with Fourier transforms, right? So I will give you a brief refresher when the time comes, but I'll assume that at least you have taken an undergraduate course in which you have been introduced to Fourier series and Fourier transform, right? Okay, so what else? What else are you going to learn in this course? We'll go back to the same example again. So let's say this is an example where two persons are trying to communicate, but as you know that there are more than two people in this world, right? Should not be a surprise, but then let's assume that there are multiple people in a field or in a classroom or any closed settings, and there are multiple people who are trying to talk to each other, then what's going to happen? They are not necessarily talk A is, I mean, it's not necessarily that all of them are trying to talk to A or B. Let's say A is trying to communicate with B, but there are other C, D, E, F, G. There are multiple people who are talking to each other. Then what's going to happen? So obviously, you will see that it doesn't. This example, from this example, you should be able to understand that it will create a lot of chaos, right? But let's assume that they are not talking at the same tone, right? What did we say? We said that they are probably not. All of them are probably not talking at the same tone. So then, is it possible? Is it possible for A or B to distinguish their voices with respect to the others? In principle, even though the example of human voice is probably not a very good example in this case, because all of us kind of have similar tones, unless you are a trained singer. But from this example, you should be able to probably appreciate the fact that if we can probably distinguish one tone from another and have a mechanism of filtering out the desired tones from the other, then there is probably a chance that I should be able to tune into whatever B is saying, or B should be able to tune into whatever A is saying, while not concentrating on anything else that is being thrown to us. So in other words, in this congested environment of electronic devices, we must know how to filter. We must know how to filter a circuit, filter out of band noise, and get the desired information out. So we need to have some rudimentary idea of how a filter works. So we'll talk about filtering, right? We'll talk about certain types of filtering. What else are we going to learn? We're going to also learn about something which is not particular to, I cannot give the example of human communication in this case, or we cannot give you the example of A trying to communicate with B, but as it turns out, we'll need to understand how some timing circuits work, right? For example, we need to understand how a voltage control oscillator works, or a clocking scheme works, right? So we need to understand how a clock is generate timing information, or generate clocks, and for this we require understanding of a circuit which is called a VCO, or a voltage control oscillator, and a PLL, or a phase lock loop, right? So this is the VCO, this is the PLL. Just a piece of information at this stage of the course, even though we'll be talking about VCOs and PLLs, but we'll keep it very basic. We'll not go very deep into discussion on VCOs and PLLs, but we'll try to go deeper into the other aspects of RFICs. Okay. So what else do we need to learn? So in this course also, we need to learn, when we say the part that I probably missed is when we talked about, we need to understand how a frequency domain analysis of a signal looks like. I would expect that we also know we also know how to analyze sinusoidal steady state response. Right? So what do I mean by sinusoidal steady state response? It essentially means that when I apply a sinusoid at the input, I mean, it should not be a surprise at this stage that I am applying a sinusoid as a test signal, because I have been talking about tones and tones and tones. So what is a tone? A tone is essentially a single frequency signal. Ideally, it's a single frequency signal. So if I apply a sinusoid to an electronic circuit, and I wait for some time for all the transients to settle out, how does the final waveform look like, right? So as we know, if I apply a sinusoid to a linear time invariant system, the output of that linear time invariant system will possibly have a different amplitude of the sinusoid, and it might have a different phase of the sinusoid, but it will not change the frequency of the sinusoid, right? So that is a very unique property of an LTI system or a linear time invariant system. We are going to revisit that, but I would expect that we know how to analyze a sinusoidal steady state response, which essentially means that I would expect that you know how to, you should be comfortable with Bode plots, i.e. the magnitude and the phase response, right? And phase response of an LTI system. Okay. Now, as it turns out, this will also not be sufficient. We will need to know, we'll need to do something else, how to analyze particular category of circuits which are called linear periodically time varying circuits, right? So instead of giving you this big name, let me give you an example. Again, the example that I gave you at the beginning, when two friends are trying to talk to each other, if one is trying to speak at a different tone, right? If both of them are speaking at a different tone, then there is a chance that they might be able to talk simultaneously and be able to listen to each other, right? So an electronic example of that is, let's say person A is talking at a frequency f naught, and person B is also talking at a frequency f naught. If both are talking at a frequency f naught, there is no way you can distinguish who is talking and make sense of it. But is it possible that I can transform this frequency f naught to a different frequency, right? Is it possible that I transform this frequency f naught to, let's say, f1, right? And then send this f1 to the receiver, in this case that is B, and tell B that look out for that frequency f1. If something is coming from f1, it is my own it is coming from A, right? I tell B that it is coming from f1, right? So this f naught is probably voice. This f naught is voice frequency. This f1 is a different frequency, right? So if, let's assume this, for the time being, let's assume this f1 is greater than f0, right? But B has an eardrum which can listen to only f0. It cannot receive, I mean, if f0 is, let's say, 10 hertz and f1 is, let's say, 10 megahertz, then obviously B will not be able to listen to a 10 megahertz signal, right? So what does B need to do? B, before it reaches the eardrum of B, it needs to be converted back from, so this is from, so this is f1 that is going, it has to be converted back from f1 to f0 and then sent to B. So what I should write is, in this case, I have a transformation from f0 to f1, and then as it tries to reach B, there is I transform it back from f1 to f0, and it reaches B. And let's say B also transmits something of frequency f0, but B does not transmit f0, but let's say B transmits f2, some different frequency which is not the same as f1 or f0, right? So B transforms its frequency f0 to f2. So I should write probably in a cleaner format. F0 gets transmitted, gets transformed to f2, and then this is transmitted, and before it reaches A, it gets again converted from f2 to f0, and it reaches A, right? So if that is the case, through the channel, right? So this is the channel, this is the media, this is the wireless media over which over which this entire transmission is taking place. Let me not put the wireless media there. Let me put the wireless media here, right? So this is the channel, right? So what is getting transferred through the channel? So here frequency F1 is getting transferred, and here frequency F2 is getting transferred, right? So at the interface, right, both A and B are receiving different signals, and but they can possibly transfer it down to the frequency of interest. Okay, so again, if you do not, if this is sounding vague at this stage, it's okay, let it be, right? So when we talk about this kind of circuits in a later class, it will possibly become clearer. But the key thing from this example is, let's say I am not in the channel, I am not using the same frequency for transmission and reception, then possibly I can both transmit and receive at the same time and without any loss of information. But in order to do that, I either have to speak in a different tone or find a way of transferring my voice to a different tone. And that transferring of voice to a different tone requires a special class of circuits. They are called mixers. So we'll be learning about mixers. Also in this course, we'll be learning about mixers. Mixers are the class of circuits, one kind of circuits which can transform one frequency to another, right? So it transforms one frequency to another, or there is the more technical term is it can help in modulation. It modulates, helps modulate a sinusoid or a signal of a certain frequency to another, right? And as it turns out, mixers are an integral part of any RFIC signal chain, and we will also learn about mixers in some amount of detail, right? Oh, what else? Now, as it turns out, there is RFIC is a very jargon heavy course, right? So I mean, if you look into any RFIC papers or textbooks, you are going to see a lot of jargons like P1 dB, B1 dB, IIP3, and so on and so forth, right? So we'll try to demystify the jargons and help understand the physics behind each of these terms. However, there is one thing that we need to be very comfortable with, and that is the unit of decibels. Now, the reason we need to be comfortable with the unit of decibels is as follows. The example again that I gave you of two friends trying to talk to each other. Now consider the friend that is at the other end of the field, he is trying to shout at the top of his voice, right? And the friend who is trying to receive is probably receiving a very attenuated version of that sound. So what is the difference of amplitude? What is the difference of power that the transmitter is sending and the receiver is receiving? There's a huge difference of power, and the difference of power, you'll be surprised, can be as high as 9 orders of magnitude, can be as high as, if you are considering power, it can be as high as saying that I am transmitting probably hundreds of milliwatts of power, but I am probably receiving few nanowatts of power, right? So you can see there is order of 10 power 8, order of 10 power 9 kind of difference in power, right? So we deal with, so RF circuits are exposed to large variations power levels of the order of almost from nanowatts to milliwatts or other hundreds of milliwatts, right? So when you have such a variation of power level, or rather when you are dealing with numbers who have such large variation, while you are dealing with numbers which is as small as 10 power minus 9 to as high as probably 1, right? So what is the best way to deal with these numbers? Linear scale is simply too messy. You have to write 10 power this, 10 power that all the time. So you deal with in log scale, right? So essentially we deal with decibels. So you need to be comfortable with decibels, right? We should be also be comfortable with decibels or dB. And as it turns out, most of the almost everything in RF, when we talk about RF's amplitude, RF power, with anything and almost everything in RF is expressed in dBs. It is rarely expressed in terms of watts or milliwatts or volts or millivolts, and we'll get comfortable with dealing with these topologies, right? Fine. So with that, let's stop here. I'll see you in the next lecture where we will start off with one of these topics, right? Uh, and and we'll see. I will take it from there, right? Okay.